So in this video we will be understanding how to set up Librelane with PDK. Either it is the Sky 130 or any open source PDK you want to use with this tool. So first we will search Openlane on Google. So there you will see this Openlane repository. So as you can see, Openlane is currently in maintenance mode, and they have given the link to their updated version of Openlane, which is Librelane. Just click on it. So you have reached to the Librelane repository. Don't forget to start it. So now have a go through it. So it's a ASIC infrastructure library based on several components including OpenLane, YOSS, Magic, NetGen, CVC, K-Layout, and a number of custom scripts. Now for this you need a Python installed on your PC, and you need so it is recommended to install the Nix based installation. So just click on this. So just this is the Librelane documentation. Here you will find everything in detail on how to use Librelane. So this is the Nix based installation. So we are using Ubuntu here. So just click here. Follow these steps. So you need these requirements. This is the minimum needed, and if you have this requirements PC, then it's very good. But if you don't have it, no issues, you can still do projects on your PC. Now first you have to install Nix. So just click on this, just type this in your terminal. So I will do this. I will create a folder for it here. So as you can see, I already have the Librelane folder here, but I will teach you how to install it from scratch. So I'm typing up the name of this folder. So I'm naming it PD projects. So we will do the installation here from scratch. So just click just install this card. So it's already installed. Now next you have to run this. And after installing Librelane, so after installing Nix, you have to clone this repository, this Librelane repository on your PC. just copy it and clone it. So it will take some time. So now we will be enabling the next shell in the terminal. So open the terminal in your home directory and as you know, my Librelane is this directory. So we will run this command. So ensure that you have good internet connectivity when running the next shell, otherwise it will throw these errors. So now we are into the next shell. Now next we will be into the we have to go into the Librelane ID. We have to go into the Librelane folder. So cd Librelane, yes. So we have got into the Librelane folder. So now if we want to do the smoke test, so for that we will have to do this. We have to run this command. So now we will be doing the smoke test. So for that we have to run this command. So now run it. So it is fetching the PDKs. So it will take some time. As you can see, flow is in the process. It's running all the things, CDS, placements, floor planning and everything is going on. So our first test is successful. Now if you want to create your own custom design and do the GDS with Sky 130, so I will tell you the process for that. So now here we have created a design directory. So as you can see, I have created this my designs directory. Here there are various different designs, so you can create your own folder whatever design you are making. So as you can see here, this is STM design. Here is the SRC folder where you will keep your SDC files and your design. And here is the verification, like you have to put your test bench here your Coco TV test bench, whatever you are making. And this is the pin config file. These are the pins, as you can see in the design here. So these are the inputs and outputs of the SPM design. So based on these inputs and outputs, we create this pin config file. Now this is our config.yaml file. So here we have defined where is our top file, where is our SPM file. So as you know, we have our design name is spm.v, so we will accordingly name it. So save it, and so here are the technology specific overrides. So you can use the global foundries 180 nanometer PDK or Sky 130 nanometer PDK. So now we will run the GDS flow of this design. So for running the GDS flow, as you can see, they have given the tutorial also for this SPM design. For this PM32, actually this PM32 is 32-bit parallel multiplier. So they have given tutorial for these two designs, PM32 and SPM. So you can go through this. So you have to go to the directory of the My Designs folder. So as my directory is in the home page, so I will go there. So now we have gotten to the directory, and now we will run our design. So in our so you can run any design like PM32 or SPM. So we will go with PM32, but this folder is empty. So if you want to download this, so then the RTL content. So this is the PM32 design, you can see, which is given by the Librelane documentation. So let us create our design directories from scratch. So we will copy these folders from the SPM and we will copy into PM32. So now we will have to modify all these according to our PM32 design. So we will copy this code of the PM32 design and paste it here. So we will rename it to PM32. So now we will break down the config.yaml file used for the PM32. So PM32 is a 32-bit sign multiplier that uses a sign partial multiplier, or you can say the SPM block. So this configuration file tells the physical design tools how to interpret our Verilog, what constraints to apply, and how to floor plan and route the design. So let's go section by section. So first is the basics. So first of the basic section, so here we define our top level design and RTL files. So this is our PM32 design and SPM. So as you can see in our PM32 design, this is our PM32 and we have instantiated the SPM also here. So now let's move on to the config file. So Now the next section we will move on. So next we define the clock and reset configuration. As you can see here, we have defined the clock and reset. So clock port is CLK, as you can see here, and the clock period is set to 10 nanoseconds, meaning we are targeting a 100 megahertz clock. So the reset port is RST, and we have set reset is active low to pause, because in our Verilog reset is active on the positive edge, not active low. So these settings are super important for synthesis and static timing analysis, since they define the base, frequency, and reset behavior of our circuit. So then we have optional SDC files. So these are known as synopsis design constants file, like implement.sdc and sign off SDC. So you can use these to add detailed constraints such as input and output delays or multi-cycle paths. Think of them as fine-tuning knobs for timing. So next we move to the power distribution section. So now the PDN, or we can say power distribution network parameters. So these values define how power rails are distributed across the chip. So the spacing, width, and pitch of the VDD and GND stripes, ground stripes. So for a small macro like PM32, these defaults are 5 microns offset and 30 microns pitch are perfectly fine. Now next, we move to the pin configuration. As you can see here, this is the pin configuration, and under the tool or flow helpers we point our simulation test bench, which is the TDPM32.B. So this helps integrate simulation into the same flow, so you can test both RTL and post-synthesis version. So finally we reach the technology specific overrides. So this section lets us adjust settings based on process mode. For example, Skywater 130 or GF Global Foundries 180. So for Sky 130 we set a core utilization of 45% and maintain a 10 nanosecond clock. For high speed library we even relax the count clock period to 8 nanoseconds. For Global Foundry 180 we lower the target density to 50% and set a longer 24 nanosecond clock period. So the flexibility makes the same design portable across multiple fabrication technologies. And let us now move on to the pin config file. So now we will be creating the pin config file. So as you can see, this is the pin config file, and how to create this. For that I will show you an image. So this is how our pin will be placed. So the north is for the outputs, south is for the inputs, and the center is for the processing. So we have placed the clock, we say start and done in the east. So this is how we have created a pin config. Let's save it. Now we will run our GDS flow. So, as you can see, our flow is successfully running. So our flow is successfully done. Now we will look on the GDS. So we have run this command. So now we will check the GDS too. So it is config.yaml. So this is our PM32 design GDS. So we can also view the layout in OpenRoad. So just copy it and paste it here. So with this we have completed the GDS of this design, and in next video we will see how to add any other open source PDK apart from Sky 130. Thank you for watching.